Just wait for a few minutes. I think some people are joining. Yeah. So the curves which are there for the describing the motion is what is the x versus t curve? X versus t curve. And the second was the velocity as a function of time. And the third one is acceleration. Okay. And velocities d for 1D motion is dx by dt. And acceleration is dv by dt. Okay. So if we take the x versus t curve, xt curve, and take the derivative, which is the slope, I'll get the velocity. So let me take a simple case, say falling under gravity, where its acceleration is constant. Okay, acceleration is downwards, right? So let me this minus g. So from here I get the velocity as the integral of a dt. And the integral is nothing but the area under the curve. So here, when it keep on increasing time, the area will keep on increasing. Okay, so the velocity will go like this linearly. And similarly, I can say x is integral of v dt. Okay, so this area will also keep on increasing as time increases, but increase like this. Another thing is the derivative of x of t curve is the velocity. So the slope of x of t curve, v is slope of xt curve, because the geometrical meaning of the derivative is slope. So if we take the slope of v versus x curve, or sorry, v versus t curve, it will be acceleration. It should be t. Derivative of velocity is times acceleration. So here the slope of the time is like this. Here the slope is like this. Here the slope is like this. So the slope is getting steeper and steeper. So the slope as time increases is increasing. So velocity is increasing with time. That's what is happening here. The velocity is increasing with time. Okay. And if you take the velocity curve, the slope here is constant because velocity of a straight line is constant. The slope is constant everywhere. That's what is happening here. Okay. I have to draw it properly. Because here I put the thing as negative, right? So actually this velocity should be like this downwards. Then the slope will be negative. Okay. And that slope will be minus g. Okay. So if you want to be consistent with this, then the acceleration, instead of taking acceleration as minus g, the acceleration will be plus g. So here the positive slope. So this velocity curve is corresponding to this acceleration curve and also corresponding to this displacement curve. Okay. So if the velocity is going down, here the velocity was increasing with time, right? The previous one. So suppose I make it decreasing with time, v versus t. So decreasing with time. Okay. So the corresponding xt curve, the slope should keep on decreasing. So here it should be like this. So here the slope is some value. It's steep here. It's becoming flat. So finally it's becoming zero. So this point where the slope is becoming zero will correspond to this point. When V versus T curve is a straight line, VT curve is straight line. XT curve will be parabola. So straight line means V equal to some number into T, right? And V is dx by dt. So from this I get x as integral V dt. So integral, when I integrate T, it will become T square. So that's why when V versus T curve is a straight line, this x versus T curve will be a parabola. Because parabola is T square plus some T plus some constant. And the parabola can be of two types. One type of parabola is U, another type of parabola is inverted U. The difference between these two is in this U parabola, the slope initially it's like this, and here the point slope is 0. After it is like this, like this. So here it is 0, some positive value, and the positive value here is more. So here the slope is increasing. Here it's negative, but large negative. Here it's negative, but small negative, and it's 0. So if you take from here to here the whole thing, the velocity is constantly increasing. If you assume this is XT curve. Similarly, for the second one, here the slope is positive maximum, and the positive less, and here it is 0, and here is negative, and here is negative maximum. So here is positive, less positive, 0, and small negative, and then large negative. Here it is small negative, negative slope, because the line is going down, and here is large negative. So here the velocity is decreasing. So since here the velocity is decreasing here, this one, so it will be inverted parabola, because the inverted parabola corresponds to decreasing velocity because the slope is decreasing. So increasing velocity will correspond to U parabola. Here the velocity is increasing, so the corresponding parabola, which is the x versus t curve, will be a U curve. You will get U, but when the velocity is decreasing, it will be inverted U. So here the velocity is more. Okay, so the slope should be maximum. Here the velocity is 0, the slope should be minimum, and the minimum slope is 0. The acceleration for this curve, it's since it's a straight line, it's constant. Here will be negative, and for this curve, if V versus T curve is like this, here the acceleration will be positive. So under gravity, falling into gravity, acceleration is constant. So depending on which direction you choose as positive, either acceleration will be plus g or minus g. If you take upward direction as positive, then acceleration will be minus g. And if you take downward direction as positive, then the acceleration will be plus g. That is just a matter of convention, but whatever you choose, just be consistent with that. Doesn't matter what you choose, which direction is positive. And cross product of two vectors, A cross B. So A cross B by definition is A into B into sine theta, and there is some direction. Okay, and theta is the angle between the vectors A and B. This is vector A, this is vector B, and this is the angle theta between them. So it is defined as, it's by definition. In another question, it's by definition, A B into sine theta. So from this I can figure out that this A cross B will be 0 whenever theta is, it will be 0 whenever theta is 0 degrees or 180 degrees, two possibilities. Because sine 0 is 0, sine 180 is also 0. So these are parallel vectors, like A and B are same direction. Here, one vector will be like this, another will be like this. These are anti-parallel vectors. So in both cases, the cross product will be 0. Similarly, A dot B is defined as A into B into cos theta. And it's a scale, there's no direction. So this dot product will be 0 when theta is 90 degrees. So when force is perpendicular to the displacement, there will be the direction of displacement, say ds. Here the work done is 0. Example is uniform circular motion. The force will be towards the center. but the velocity and the displacement direction is tangential. So the angle between the force vector, centripetal, and the direction displacement is tangential, is 90 degrees. So first work done during the uniform circular motion is 0. Okay, so just leave this one. Let's focus on cross product. So A cross B is AB sin theta, and B sin theta is vertical distance. So this vertical distance is B sin theta. This vertical distance is B sin theta. That's from this right angle triangle. Okay, so if we take half into A into B sin theta, so I can complete this triangle. So this will be the area of this triangle. Area of the triangle which is shown here. Okay, this triangle. So from that I can say A cross B is area of parallelogram, because I can complete the parallelogram like this. This should be parallel to A, and this parallel to B. So this is the parallelogram. There are two triangles. One triangle is this one, and the second triangle is this one. So two triangles will give the area of the parallelogram. So area of this is A cross B is area of the parallelogram. So if they ask you to derive or show that area of a triangle formed by A and B is half of A cross B, this is the proof. Area of a triangle formed by A and B is half of A cross B. To prove that, this I can write as half of AB sin theta. So if we take A as B, A as the base of the triangle, B sin theta is the height of the triangle. So this is nothing but half into base into height, which is nothing but the area of the triangle. So you can prove that area of a triangle is half of A cross B. Momentum is conserved when there is no external force acting on the system. So let me consider my system as system of two masses, M1 and M2. Okay, so there is no external force acting on this. So the momentum, initial moment of the system, let it, the initial velocity be U1, U2, and let them collide. And after collision, let the velocities become V1 and V2. So initial moment of the system is Pi, which is M1 U1 plus M2 U2, and the final moment of the system is M1 V1 plus M2 V2. Since momentum is conserved, then there is no external force acting on it, so these two will be equal. So given M1 U1 and M2 U2 and also V1, I can find V2. So this is called conservation of momentum, and so if we do something like there is a wall here, and there is some mass coming and hitting it at an angle. Okay, and after colliding with the wall, it will go like this, and the velocity is given say 5 meters per second, and this say angle is say 15 degrees. I can find the impulse on this mass. Suppose this is a ball or some mass. So the impulse on the mass by definition is change in momentum. Here in this will be final momentum minus initial momentum, and momentum is a vector. Okay, so the initial momentum is, final momentum is this 5 in same 15 degrees. Okay, so this also 5 meters per second. So final momentum is the mass into the final velocity. So this velocity u I can write as in component form will be u f cos 15 in the I cap direction. This is my x-axis, and this vertical direction is the y-axis. So this incoming velocity, this velocity, I can split into two components. One is the horizontal component, this one, which is phi, or a phi cos 15, because this angle is also 15 degrees. So with phi cos 15 and the direction is I cap, and the vertical component is phi sin 15 the j cap. This phi sin 15 degrees in the j cap direction. But the v, the final velocity, v, the x component is minus phi cos 15 I cap, but the vertical component is upwards only. So f sin 15 j cap. So this final velocity, which is this one, okay, the horizontal component is towards left. That's why it's minus I cap. But the vertical component is still upwards. So it is plus j cap. Okay, so this change in momentum, it will be final minus instance will become minus phi cos 15 I cap minus this initial, again minus cos 15 I cap. So it will be minus 10 cos 15 in the I cap direction. J component will cancel because these two are equal. Both with this J, so those two will cancel. So the impulse will be along the I cap direction. And you take the component. Mass is missing, right? It's mass into moment is mass into velocity. So it's this is the velocity. So I have to multiply with mass. Mass will be given in the question. So from that I can find the impulse exerted on the ball. So instead of ball, I can have a bat also. So instead of saying I have a ball where the ball is hitting, I can have a bat, and the ball is coming and hitting this bat and is getting going like this. So here the impulse on the bat or on the ball, it's again same delta P. Analysis is exactly same like this one, previous one. So they will give the initial velocity and the angle, so you can find the impulse. Okay, perpendicular axis theorem already said, is there in the book. The basic thing is Pythagoras theorem. This is a perpendicular axis. So there is it's applicable for bodies which are in the, what do you say, they're 2D bodies. So this is like a disk in the XY plane. So it cannot be and the disk has to be flat in single plane, XY plane. So even if you bend this plate, this perpendicular axis theorem is not valid. So it's valid only for a flat plate. So moment of inertia of this flat plate about this z-axis, it is the moment of inertia about the x-axis and y-axis. So this is a plate which have a moment of inertia of the x-axis, that we call it Ix, and moment of inertia of this plate about the y-axis, that will be Iy. So that is related to Iz as Iz equal to Ix plus Iy. Okay, this is perpendicular axis theorem. And this comes from Pythagoras theorem, which I already explained. So this is for 2D bodies, and the plane of the body should be a flat plane. Parallel axis theorem is for a 3D body. So we have suppose I want to find moment of inertia of this object about this axis. So I'll take a parallel axis passing to the center of mass. This O is center of mass. So if I know the moment of inertia of this body about the center of mass axis, I can relate this. I can get this moment of inertia about this parallel axis by this theorem. I about parallel axis is I about center of mass plus the mass into the distance between the two axes. This A is the distance between these two axes. A. Okay, so I about the parallel axis is I about the axis passing the center of mass plus the mass into the distance between the two axes square. So using this, I can find, say this is a, is it a, okay, it's a ring. Okay, so moment of inertia of the ring about the diameter I know, because moment of inertia of the ring about the axis perpendicular to the ring is mr square, and about the diameter be half mr square using the perpendicular axis theorem. So after that, I can find the moment of inertia about this ring about the horizontal tangent. That's by using parallel axis theorem. Is this clear, or should I explain? Divya, uh, is it clear?
It's clear.
Okay,
It's clear, sir.
yeah. So I'll just say it good. Okay, the first thing for mode of inertia is for point mass m at a distance x, say this is the axis, at a distance r. For a point mass, I is defined as mr square. This you don't have to question. Using this, I can get mode of inertia of a ring of mass m about the axis is same m r square, because any element of this mass, that dm is at the same distance from the axis. So all this dm will contribute dm r square, and the total mode of inertia is summation of this one, that is equal to m into r square. So mode of inertia of this ring about this axis is perpendicular to this one is mr square. And if you want to find the mode of inertia of this ring about this diameter, use the diameter, but this diameter is in the plane of the ring. So to do that, I'll take a second diameter which is along the plane of the ring. The diameter 2, and the angle between these two diameters is 90 degrees. I can choose two diameters like this. So using perpendicular theorem, I about diameter plus I about diameter 2 equal to Iz, which is I on the axis. And by symmetry, these two are equal. They are same. So this will become 2 times I about the diameter equal to I about the axis, which is mr square. So from this, I let I about the diameter as half mr square. So here I use perpendicular axis theorem to get the I about the diameter from the I about the axis. So that's what they have used here. In this, it's a ring. So I about the diameter is half mr square. That comes from perpendicular axis theorem. And using parallel axis theorem, I about the tangent is I about the axis passing the center, which is half mr square, plus m into the distance between the two axes, which is r. So mr square. So using parallel axis theorem, I get the I about the tangent. Horizontal tangent is 3 by 2 mr square. Okay. So similarly, if you have a spherical, okay, for a disk, solid disk, which is not a ring, the moment of inertia about the vertical axis is half mr square. For a ring, it is about the axis mr square, because here the mass is farther distance. Because I is nothing but the mass into the distance square for a small mass. But here the mass, all the mass at the larger distance of r. But here some mass is nearby. So I of this disk will be less than this I of the ring. And the disk factor is half. And for this disk, I can get the I about the diameter by using perpendicular axis theorem. I about the diameter will be half of I about the axis will be 1 by 4 mr square. And once I get this about the diameter, I can get about the tangent by using parallel axis theorem. That is I about the center, that is 1 by I about the diameter plus mass into the distance between the two axes, that is r, mr square. Then similarly, you can have moment of inertia of a sphere, solid sphere. Okay, about the one which is passing through the center. And similarly, I can have a spherical shell. Okay, and moment of inertia about the axis passing through the center. Okay, so this I, the mass will be the same. So I of this spherical shell will be moved because here the mass, all the mass is a distance of r from the axis. Sorry, not exactly r. It's a larger distance. So this mass at a distance r, and this mass at a distance less than r. But here, this mass at a distance r, but this mass at a distance less than r. This one distance less than r. But it's the same amount of mass in both the cases. So in the spherical shell case, the amount of inertia is 2 by 5, 2 by 3. 2 by 3 m r square, r is the radius of the shell. But in the case of solid sphere, it will be less than this one, and that factor is 2 by 5. 2 by 5 m r square. So once I know this thing, I can find I about the tangent. Tangent by parallax theorem will be I about the axis plus this distance. What this is with the r. So I about this tangent will be this 2 by 5 mass square plus the mass the distance square. Similarly, here the tangent here about this tangent will be this one plus mr square. I of a sphere that is 2 by 5 mr square. I of a spherical shell will be more, that is 2 by 3 mr square about the diameter and the tangent. Okay. So center of mass of a disk with a hole. If a spherical shaped disk means the 2D objects are flat disk. Okay. Suppose a full solid disk by symmetry, center of mass will be at the center. Okay. But suppose in this I put a hole, same disk, but I put a hole here. Okay. So now the disk is only this much, this outer part. There is no mass in this here. So now the center of mass from the center will get shifted towards here. Okay. So to find the center of mass, I can use one concept. So this disk with the hole is equivalent to your disk without the hole disk, plus a disk of negative mass corresponding to the cavity portion or the hole portion. So mass is distributed around the flat surface. So let this mass density be sigma. That is equal to total mass by area. Okay. So the unit of this thing is the mass kg per meter square. So this is like surface mass density. Volume mass density is kg per meter cube. But this mass density, surface mass density, like I'm taking the mass and distributing over the surface. So it will be kg per. So this is the same sigma. And this sigma, it's a negative mass minus sigma. Okay. So when I place this, when I combine this minus sigma with this plus sigma, it will give me a disk with a hole. Okay. So to find, instead of finding center of mass of this this one, I can find center of mass of this object. This one that will be at the center. Okay, and the center of mass of this negative mass disk that will be at the center, and I can find center of mass of this combination to get the center of mass of the disk with the hole. So let me do for a concrete example. Suppose this.
I didn't understand that, sir. Can you just explain once again?
Yeah, I'll come back to that. Just a minute.
Okay, sir.
I'll tell you. See, this is a disk with a hole. Okay, there is a hole here, and it's a disk with a flat object, right? So I can have a surface mass density associated with it. So I just have to take the total mass and divide it by the area. So let this mass density be sigma. The unit will be kg per meter square. Okay, so this disk with a hole, I can think it's made up of a solid disk without the hole with same sigma plus a small disk with negative mass. Okay, so if you place this disk here, that will create me a hole. Because plus sigma and minus sigma will cancel at this point. So this concept is clear. Just accept it. We'll see why is it.
Yes, sir.
Okay, so now let me use it. So if this is a disk of radius r, and there is a hole of this much size. So radius of this thing is r, and the radius of the hole is r by 2. Okay, so this is equivalent to a disk without the hole of radius r, and corresponding to the hole, I have a negative mass. So this plus sigma and this density sigma. So plus this one. So the center of mass, this object is at the center, instead of this is the center, but this mass is will be called the M1, and this is M2, which will be a negative mass. And the location of this M1 center is this point. And the center of this second mass is here. Okay, so if we take I can take this also, origin of x-axis. This is my x-axis. So the center of mass of this one will be, the center of mass is 4 will be r comma 0, or I can just make it r. And the center of mass of this one will be, this coordinate will be r plus r by 2. That is 1.5 r. Okay, so this M1 is at r and M2 is at 1.5 r. So the center of mass x is M1 r1 plus M2 r2 by M1 plus M2, this by definition. So M1 R1 is capital R plus M2 1.5 R divided by M1 plus M2. And M1 is sigma into pi R square. And M2 is negative mass, it's minus sigma into pi R by 2 square. Okay, so this will become okay, sigma pi will cancel, so it will become R square into R plus M2 is minus so I have cancelled sigma into pi factor everywhere. So bottom also sigma pi factor will go, it will become R square plus 1 by 4, but it's minus sign here. So it will be 3 by 4. So it will be 3 by 4 R square. Is this clear? This R,
Sir.
this R. Okay, and M1 is sigma pi into R square. I'm leaving at sigma pi because it will cancel. So only R square is remaining that I put here. Similarly for the second one, 1.5 R I kept it here, and M2 is sigma pi I'm leaving, so it's become minus R by 2 square, that is R square by 4. And M1 plus M2, I'm leaving on start to sigma pi because sigma pi will cancel. So R square plus 1 by 4, but negative sign is there, so it becomes 3 by 4 R square. Okay, so from there I get the center of mass of this object with the hole. So the center of mass will be somewhere here. The basic idea is something object with a cavity or hole is equal to the object without the cavity plus corresponding to the cavity have a negative mass. So center of mass of this thing is center of mass of this combination. The center of mass of two masses is m1 x1 plus m2 x2 by m1 plus m2. And by symmetry, center of mass of this will be at the center. This will be at the center, but only it's a negative mass here. Okay, so you have to use that thing. Is it clear?
Yes, sir.
Okay, so conservation of angular momentum, like linear momentum is conserved. Linear momentum is m into v. So when there's no external force, when the external force acting on the system is zero, then momentum is conserved. Then we can say final momentum is same as initial momentum. This is in the translation motion. So in the rotational motion, something called angular momentum, which is defined as R cross P. Okay, so if external torque instead of external force, when the external torque is zero, then the angular momentum final will be same as the angular momentum initial. So one example is sorry, this is the one. See, here this person is spinning on this chair. Okay, so there is no external torque acting on this because it's a smooth, whatever, rotating part. So when the arm is stretched, I has increased, right? Because I is nothing but mr square. If the mass is far away from the axis, then I will increase. So when the arm is stretched, I is more, and angular momentum is I into omega. If there is R cross, it will come out to be I into omega. So when I is increasing, omega will decrease as the product is constant because L is conserved. Okay, so when the person's arm is stretched out, I will increase because mass at a larger distance. So when the arm is stretched out, this omega will decrease. So this person will speed will reduce. So when the arm is brought nearer to this person, then I is decreasing, so omega will increase. So this is conservation of angular momentum. So similarly, if you have a disk which is rotating, about an axis, okay, and there is some small mass here, okay. If I move